the packaging line used to place chips side by side like tiles on a floor. Then the industry flipped them face to face, stacked them directly on top of each other, and connected them through bonds thinner than a human hair divided by 1,000. That move, called hybrid bonding, became the gating step for every high-bandwidth chip stack being built today. And for years, the tools that perform it came from two companies, a Belgian firm called BESI and an Austrian firm called EVG. No qualified domestic Chinese alternative existed until Naura's HPD30 passed customer verification. Before you file this under China hype, understand that one tool passing customer verification is not volume production, and it is certainly not leading-edge pitch parity. Both of those caveats matter, and we will get to exactly where the limits are. But the stakes here are real. Hybrid bonding is not a niche process. It sits underneath high-bandwidth memory, under the chiplets in high-end artificial intelligence accelerators, under the stacked image sensors in every flagship phone camera. Whoever controls the tools that perform it controls the geometry of what gets built. By the end, you will understand what hybrid bonding actually does, exactly where Naura's tool plugs into the packaging line, what it still depends on, and why the floor China just raised is not the same thing as the ceiling it still cannot reach. And the word verified is doing a lot of work in this story. We will map precisely what it means and what it does not. There is also a third company in this story, and it is not where you expect to find it. Applied Materials sits in this picture, but not at the bonding step. This is not a story about one bonder. It is a story about a packaging stack, a precise sequence of steps so intolerant of error that clearing one node changes what is possible, while the nodes above it still define what is best. To understand why clearing this one node matters, you first need to see what hybrid bonding actually does, and why it is the hardest step in the whole packaging sequence to replicate. The old approach to connecting chips was wire bonding and flip chip. You joined chips through small solder bumps, spaced microns apart. The bumps created physical distance between surfaces, and that distance capped how fast signals could travel and how much heat could escape. Hybrid bonding removes the bumps entirely. It creates a direct copper-to-copper bond between two surfaces, with no solder in between. At the leading edge, the pitch, the spacing between those copper connections, falls below a few microns, and the frontier is pushing toward sub-micron territory. That shrinking pitch is why the bandwidth gains are so dramatic. More connections per unit of area, each one shorter, each one carrying more data with less power lost as heat. But the physics that make hybrid bonding so powerful are the same physics that make it so difficult. The two surfaces being joined must be flat to within a fraction of a nanometer, not a few nanometers, a fraction of one, across a wafer that is 12 inches wide. And the alignment between the two surfaces must hold to sub-micron tolerances at every point across that entire 12-inch span. The error budget does not accumulate graciously. One misaligned micron, repeated across thousands of bonding sites, and the bond breaks down. Think of it like welding two mirrors together, face to face so perfectly that no light leaks at the seam. Except the mirrors are 12 inches across, the weld happens at room temperature, and one misaligned micron across the whole surface breaks the bond. That is what hybrid bonding asks of the tool. This is why high bandwidth memory and artificial intelligence accelerators depends on hybrid bonding. Stacking memory dies on top of logic. Dies with that density of interconnection is what enables memory bandwidth an order of magnitude higher per unit area than traditional packaging can deliver. The physics are not optional. You either have the tool or you're limited to older architectures. So Naura's engineers had to solve the mirror weld problem domestically. And here is something worth knowing about who Naura actually is before we talk about what they built. Surface flatness measured in fractions of a nanometer does not come from the bonder alone. That detail matters, and we will come back to it when we trace the steps upstream. Naura is not a startup that decided to take on BESI and EVG. It is China's largest domestic semiconductor equipment company, with established product lines in chemical vapor deposition, etch, and physical vapor deposition tools. Those process families are not the same as hybrid bonding, but they represent real institutional knowledge about precision process control, contamination management, and the kind of calibration discipline that running a semiconductor tool at production requires. The HPD30 is a 12-inch die-to-wafer hybrid bonder, and 12-inch matters because that is the wafer size the production industry actually runs. This is not a tool built for research wafers. The die-to-wafer configuration is also specific. It means individual known good dies are bonded to a full wafer rather than bonding two full wafers to each other. That is the configuration you use for chiplet integration, where you are assembling different functional blocks into a single package. It is distinct from wafer-to-wafer bonding, which is a different tool class with different trade-offs. Now, customer verification in semiconductor equipment has a precise meaning. It is not a lab demonstration. When a customer verifies a tool, they run it on production wafers, measure the output against specification, and sign off that the tool meets the bar required before placing volume purchase orders. It is a necessary gate on the path to production deployment, not the finish line. It tells you the kitchen is real. It does not tell you how many covers they can run on a Friday night. Naura reported that the HPD30 passed customer verification. That is a company claim, and no independent confirmation of production volumes appears in the available record. The distinction between verification passed and confirmed volume production is exactly the gap that matters here. But clearing verification is also not nothing. A lab demo that never touches production spec is a different category of achievement from a tool that passed the customer's production qualification gate. So who is Applied Materials in this story? Here is the setup. Applied Materials does not make a hybrid bonder. Its leverage in this picture sits one layer below the bonding step entirely. Hold that. We need to trace the full sequence first. The bonder does not operate alone. Hybrid bonding is the middle act of a three-act sequence, and the bonder is only as good as what comes before it. Act 1 is surface activation and planarization. Before two surfaces can form a direct copper-to-copper bond, they must be polished to sub-nanometer flatness and chemically activated so the copper and the surrounding dielectric oxide are in the right state to fuse. This step is called chemical-mechanical planarization, and it is not a gentle process. It uses a slurry of abrasive chemistry pressed against a spinning wafer to remove material with atomic precision. The surface roughness that comes out of this step has to be below roughly half a nanometer. If it is not, the bond either fails or performs at lower yield. The incumbents in chemical-mechanical planarization equipment are Applied Materials with their Mira and reflection platforms and Ebara of Japan. This is where Applied Materials lives in the story, not at the bonding table, but in the prep kitchen. China has domestic chemical-mechanical planarization tools from companies including CETC and Naura itself. But at the highest grade, where surface flatness is everything, the slurry chemistry and some of the equipment still partly rely on imported sources. That is the input-sourced assessment, some imported at the highest grade, not fully closed. Act 2 is the HPD30's job: alignment and bond. Act 3 is anneal and metrology. The bond is thermally cured and then inspected. The domestic and import status of the post-bond metrology step is not fully established in the available record, so the honest framing is that this sits within the broader picture of a maturing domestic stack. The sub-micron alignment metrology that feeds the bonder, the measurement systems that tell the tool exactly where each die is before the bond is made, is described as still maturing. Partially domestic capability, not fully closed. And this is where the surface flatness loop closes. The fraction of a nanometer requirement that makes hybrid bonding hard is not just a spec the bonder has to meet. It is a spec the surface prep step has to deliver before the bonder ever touches the wafer. If the polishing compound, the finest grade, still comes partly from outside the building, then the bonder's performance is partly dependent on that outside input. The tool running on partly domestic, partly imported surface prep can still produce verified, production-worthy bonds. The question is at what pitch and with what yield. At the finest leading-edge pitch, where the tolerance tightens to its absolute minimum, the imported inputs carry more of the burden. Which brings us to the ceiling, and to closing the loop on what verified is actually doing in this story. Customer verification tells you the tool can produce conforming bonds at the pitch the customer tested. It does not tell you it has been tested at the finest pitch BESI and EVG currently achieve. And the available record is explicit on this point. The leading edge pitch, the finest face-to-face wiring, remains the wall. BESI's, die bonder platforms, and EVGs. Wafer bonding systems carry years of leading-edge process recipe development. Process recipes, the specific sequences of temperature, pressure, chemistry, and timing that produce a conforming bond at a given pitch, are not transferred when a tool spec is published. They are accumulated through production runs, failure analysis, and iteration. That know-how gap is real, and it is not closable by delivering the hardware alone. No independent benchmark comparing the HPD30's pitch capability to BESI's or EVG's. Leading-edge specifications appears in the available record. No confirmed production volumes. No confirmed pitch at which the customer verification was conducted. The honest scope of the claim is a 12-inch die-to-wafer hybrid bonder passed a customer's production qualification gate. That is a real threshold. It is not the frontier. Now, here is the answer to the applied materials loop. Applied materials is not the rival at the bonding table. It is the supplier of the prep kitchen. Naura built its own bonding table. The prep kitchen is still partially rented. Those are two separate facts, and conflating them would misread where the dependency actually sits. Does the HPD30 matter if the leading edge pitch is still the wall? Yes, and here is why. Most of the hybrid bonding volume in production today is not at the frontier pitch. High bandwidth memory stacking, chiplet integration at mature to mid-process nodes, stacked image sensors in consumer devices. These run at pitch levels where a verified domestic bonder is directly applicable. The frontier pitch matters for the next generation of artificial intelligence silicon for the most advanced accelerators being designed right now. The middle tier matters for everything being built and shipped today. Removing a single point foreign dependency at the bonding node for that middle tier is a real structural change, not a symbolic one. Advanced packaging is not a consolation prize for countries that cannot run leading-edge lithography. It is where performance gains are increasingly coming from across the industry. In artificial intelligence accelerators, in memory, in heterogeneous chiplet designs that combine logic, memory, and analog functions in a single package. When leading-edge lithography scaling became more constrained and more expensive, the industry shifted performance leverage toward packaging. China's domestic packaging industry, already substantial, with companies like JCET operating significant capacity, is positioned to participate in that shift more fully now that the bonding step is no longer a single-point foreign dependency at the mid-tier. The HPD3O raises the floor of that packaging stack. It does not change the lithography ceiling on the logic dies going into the package. Those are separate layers, and both matter. But the floor just got higher. Here is my honest read. The triumphalist version of this story. China has cracked advanced packaging and is closing in on the frontier, is not what the evidence shows. A customer verification at an unconfirmed pitch with partial upstream dependencies still imported is not parity with years of leading-edge recipe libraries. The dismissive version, one verified tool changes nothing, is also wrong. Removing the bonding step as a single-point foreign dependency for mid-tier hybrid bonding volume is a real structural change for an industry that runs a lot of that volume. My read sits between those two. China has raised the floor of its packaging stack high enough to build a self-sufficient production line for the hybrid bonding that matters most commercially right now. The ceiling, where the next generation of artificial intelligence silicon will be built, is still above it. Whether the floor rises fast enough to meet it before the ceiling moves again is the real question, and we do not know the answer yet. Every layer of this stack has a floor and a ceiling. Naura raised the bonding floor. The surface prep floor is still being lifted. The chemistry floor is the hardest to raise because it does not come from a single machine. It comes from decades of formulation knowledge built through production experience, and the leading-edge pitch ceiling is not standing still. BESI and EVG are not waiting. Here is what I want your read on. The floor. China raised with the HPD3O matters most for the mid-tier hybrid bonding volume running in production today. That is a real immediate gain for an industry that needed it. But the ceiling where next-generation artificial intelligence silicon gets built is still out of reach. So which matters more right now? The floor China can actually use, or the ceiling it still cannot reach? Tell me in the comments, and tell me why, because I think this one is genuinely close. If you want to follow exactly how each layer of this stack gets solved, or does not, subscribe. This channel tracks every node as the evidence comes in, not the press releases. A year ago, the tool that glues chips face-to-face came from Belgium or Austria. Now, one comes from Beijing. The ceiling is still moving, but the floor just got higher.